This lesson is on limiting reactant stoichiometry, and I will be using ice tables in order to solve these limiting reactant problems. So when we have a reaction that happens, often the reaction will stop when one of the reactants is used up. So for example, if you took some baking soda and some vinegar and you poured them together, the reaction would stop when either the baking soda got used up or when the acetic acid in the vinegar got used up. So the reactant that gets used up is called the limiting reactant, and the other reactant is called the excess reactant. So the excess reactant does not get completely used up. So our limiting reactant gets completely used up. And our limiting reactant then determines the amount of product that we actually can get. So this determines the amount of product. And it also determines the amount of the excess reactant that gets used up. And our excess reactant, of course, this does not get used up. In other words, we have some left over after the reaction is complete. All right, so you will know you have a limiting reactant problem if you're given amounts of both of your reactants, or you could have more reactants. If you're giving the amounts of all your reactants, then you have to figure out which one is the limiting reactant. And we're going to do that using an ice table. So for an ice table, we're going to have I, C, and E. And I stands for, I stands for, sorry about that. I stands for initial. So this is the initial amounts of reactants. And we are going to be using moles for this. We can actually use anything that has the same relationship as our coefficients in the balanced equation. So now, for now, we'll be using moles or molecules. But in our I, never will we use grams. Never, ever, ever, ever will we be putting grams into our ice table. For now, it will have to be moles or molecules. So if we're given grams, which we might, that's fine. We're just going to change the grams to moles, and we know how to do that. That's easy. Okay, C in our ice table, this stands for change. And this will be the amount of each reactant that gets used. And the amount of product or products. And again, we're going to use moles or molecules for the change. And then E stands for end. And this is the amounts at the end of the reaction. So we'll have some product that gets formed, and we'll also have some excess reactant that we have at the end of the reaction. So let's see how this works in a problem. Okay. Hold on, kids. Okay, so here's our problem. When 5 moles of nitrogen gas are reacted with 12.0 moles of hydrogen gas, how many moles of ammonia are produced and how many moles of excess reactant are left over? Okay, so first, we absolutely need to do our balanced chemical equation for the reaction before we do any calculations. All right, so we have nitrogen gas. So nitrogen gas is N2. Remember, it's a hot sprinkle. And we're reacting that with hydrogen gas. That's H2, our other hot sprinkle. And we are getting ammonia. And ammonia has the formula of NH3. Okay, so we need to balance that. So we're going to need a 2 here and a 3 there, and we only need 1 nitrogen. So there's our balanced equation. Okay, so now we're given moles of nitrogen and moles of hydrogen. We're given amounts of both of the reactants, so that indicates this is a limiting reactant problem. We're given moles, so we can go right to our ICE table. So I, C, E. So nitrogen, we have 5.0 moles, and for hydrogen, we have 12.0 moles. Ammonia, at the beginning, initially, we don't have any. The reaction has not started yet, so that gets a 0. Now, the change is these amounts, these chemicals react, and they produce product. Which one of these is the limiting reactant? So one of the ways we can do this is to test. If we use up all the nitrogen, how much ammonia would we get? And if we use up all the hydrogen, how much ammonia would we get? Whichever one is less, that's the amount we get because the reaction stops at the less amount. So sometimes you don't need to do this with mole ratio, but we're going to do it that way because sometimes the coefficients and the numbers can be tricky. So we're going to test the nitrogen to see how much ammonia we would get if we used up all the nitrogen. So this is just simple mole ratio. So X moles of NH3, set that equal to the amount of nitrogen that you have, 5.0 moles of N2, mole ratio from the coefficients, so 2 moles of NH3 for every 1 mole of N2. N2 moles of N2 cancel, 2 times 5, we get 10 moles of NH3. All right, that's how much we would get if we used up all of the nitrogen. So now we're going to do the same thing with the hydrogen. We're going to see how much ammonia, how much product we would get if we used up all the hydrogen. So X moles of NH3 equals 12.0 moles of H2. And now we use our coefficients. 2 to 3 is our mole ratio. 2 moles of NH3 for every 3 moles of H2. And then we just do the math. 3 goes on to 12, 4. 4 times 2 is 8. You get 8.0 moles of NH3. So now we compare these two. Well, at 8 moles of NH3, the hydrogen runs out. So we can't get 10 moles. This is how much we get. So this means that our hydrogen is the limiting reactant because it produces the least amount of product. It runs out first. So I like just to put a little LR on top. And that means that this is the amount that we get. This is what the change is. Our change for ammonia, we start out with 0, we get 8.0 moles. So at the end, E, we get 8.0 moles. Our limiting reactant is our hydrogen, that gets completely used up. So our change, we use all of it. So that's minus 12 moles. And at the end, we have 0. We have used it all up. So we've answered our first question, how many moles of ammonia are produced? Now we're going to figure out how many moles of the excess reactant are left over. The limiting reactant controls everything. So now we have to do one more mole ratio to figure out how many moles of N2 get used up. We need to figure out what gets used up before we can figure out what's left over. So our final mole ratio, X moles of N2 used up. And we're going to set that equal to our limiting reactant. We could set it equal to the ammonia. Either one will get the same answer. That doesn't matter. X moles of H2 times our mole ratio. So we have 1 mole of N2 for every 3 moles of H2. So that gives us 4.0 moles of N2 used up. So it's very important. This is not what we have left over. This is what reacted. This goes here. So we used up 4.0 moles. So at the end, we have 1.0 moles of N2. So our answer, 8.0 moles of NH3 produced, and 1.0 moles of N2 left over. Okay, so there are our steps. We figure out how much product each of our reactants would give us. The least amount of product is how much we get, and that the reactant that gave us the least amount is our limiting reactant. It ran out first, and then we have to do one more mole ratio to figure out the amount of excess reactant that got used up. Okay, let's do another one, a little more complicated. All right, so this one. How many grams of water are produced when 11.92 grams of ammonia and 25.00 grams of oxygen are reacted? And how many moles of excess reactant remain after the reaction is complete? All right, so I'm going to give you that chemical equation. So it is 4 NH3 plus 5O2 equals 4NO plus 6H2O. Okay, so now we're given the amounts of both of our reactants. We're given 11.92 grams of ammonia and 25.00 grams of oxygen. All right, now for our ice table, we need moles. We want to do our ice table. This is limiting reactant because we're giving the amounts of both of our reactants. And what we want to find out is our water, right? How many grams? Yeah, we want to find out the grams of water. Okay, so we need to change these grams to moles. So X moles of NH3 equals 11.92 grams of NH3 times, well, now we need to do a molar mass conversion. So 1 mole of NH3, and we have to figure out those grams. So N, we have 1 of those, H, we have 3 of those, nitrogen is 14.01 from the periodic table, hydrogen 1.008, and we get 17.03. All right, and now let's figure out what that is. So 11.92 divided by 17.03 equals, so we get 0 point, let's see, 1, 2, 3, with 4 sig figs, 0.6999 moles of NH3. Okay, now we have to change the grams of oxygen into moles for our ice table. So X moles of O2 equals 25.00 grams of O2 times 1 mole of O2. So 1 oxygen is 16, so 2 oxygens is 32.00 grams of O2. All right, so 25 divided by 32 equals, so we get 0.7813 moles. And we don't have any water at the beginning. Now the NO, I haven't put anything for the NO because the question didn't ask about it, so I don't care about it. I could calculate it, but I don't need to, so why do something that we don't need to do? Okay, so now I'm going to test each of my reactants to see which one is going to give me the least amount of water. So we're going to test the NH3 by finding out how many moles of water we're going to get from it. So X moles of H2O equals 0.6999 moles of NH3 times, and now we look at our coefficients, it's just simple mole ratios, 6 moles of H2O for every 4 moles of NH3. Okay, so 0.6999 times 6 divided by 4 equals, oops, I did something wrong there. All right, 0.6999 times 6 divided by 4 equals, all right, so we get 1.050 moles of H2O. And that is the amount we would get if we used up all of the ammonia. But as of now, we don't know if we're going to use up all the ammonia. So now we're going to test the O2. So X moles of H2O equals 0.7813 moles of O2 times a mole ratio, 6 moles of H2O for every 5 moles of O2. All right, so 0.7813 times 6 divided by 5 equals, and we get equals 0.9376 moles of H2O. Okay, so we look and see which one is less. Well, this is less. So that means the O2 is our limiting reactant. So limiting reactant. For how much water is produced? Well, that's our answer then. So here's our change. So we use up all the limiting reactants. So we can just put minus 0.7813. So at the end, we'll have 0 oxygen. We've used it all up. For the water, the limiting reactant tells us how much water we get, 0.9376. So that is gained. So at the end, so for now, these are always going to be the same numbers, but later on in higher levels of chemistry, they won't always be. All right, and now we're going to figure out how many moles of the ammonia actually got used up. Do that here. So X moles of NH3 used up equals the amount of limiting reactant that got used up, 0.7813 moles of O2 times 4 moles of NH3 for every 5 moles of O2. So let's see what that is. So 0.7813 times 4 divided by 5 equals. So we get 0.6250 moles of NH3 used up. Okay, so we didn't use up all 0.6999, we used up 0.6250. So at the end, we have 9, 9 minus 5 is 4, 9 minus 2 is 7, 0.0740 moles of NH3 remain. So now we always go back and look at our question and make sure we answer the question that is asked. So it says, how many grams of water are produced? So we've got the moles of water that are produced. So we need to just change those moles to grams. So I got to erase some of this, so I have some room here. Okay. So now we just have to change these moles to grams. So X grams of H2O equals 0.9376 moles of H2O times, do a molar mass, and we get 18.02 grams of H2O for every 1 mole of H2O. So 0.9376 times 18.02 equals, and we get 16.90 grams H2O produced. So that's the answer to that first part of the question. And then it says how many moles of excess reactant remain. So we just pull that off of our chart. So 0.0749 moles of NH3 remain. Okay, so it might seem kind of complicated, but you just break it down into steps. And once you have the idea of how the ICE table works, it's going to be so helpful when we do more advanced chemistry concepts. Okay, so if you're given grams, change them to moles. Then test each of your reactants to see how much product you would get. The least amount of product, that's how much you get, and the reactant that gave you that number is your limiting reactant. The limiting reactant gets completely used up so that you have none at the end. This product amount you get from the reactant that gave you the less amount. And then you do one more mole ratio to figure out the amount of the excess reactant that actually got used up. And then if you need to, you can change the moles that you get at the end into grams, depending on what the question asks. All right, that's it.